Hello and welcome to G Fun Facts Online. For decades, our digital world has been built on a simple foundation: silicon chips. We've lived by Moore's law, the idea that computers get twice as powerful every couple of years. But what happens when you can't shrink transistors any smaller? What happens when you hit a wall? Today, we're looking beyond that wall, at two revolutionary technologies that are throwing out the old rulebook. We're moving beyond silicon into the future of computing. First up, imagine a computer that thinks like you do. Not just calculates, but learns, adapts, and processes information with incredible efficiency. This is the promise of neuromorphic computing. Instead of copying a machine, scientists are copying the most powerful computer we know, the human brain. Your standard computer has a fundamental problem. It's constantly shuffling data between its processor and its memory. This creates a traffic jam, a bottleneck that wastes time and a ton of energy. Neuromorphic chips get rid of that traffic jam. They merge memory and processing, just like the neurons and synapses in your head. What does this mean in practice? Three big things. First, massive parallelism. Your brain juggles sight, sound, and thought all at once. Neuromorphic chips do the same. Second, they're event-driven. A traditional computer is always on, its internal clock ticking away, burning power. A neuromorphic chip only activates its artificial neurons when new information, what scientists call a spike, arrives. This is mind-blowingly efficient. Think about it. Your brain performs quadrillions of operations per second using just 20 watts of power. A top-tier GPU would need around 400 watts to do less. And third, they learn on the fly. They can adapt to new situations without needing to be completely retrained. And this isn't science fiction. In April 2024, Intel unveiled Hella Point, the world's largest neuromorphic system, built with over 1,000 of its Loihi 2 chips. It joins pioneers like IBM's True North and BrainChip's Akita, which is designed for AI on small devices. These chips are set to change everything. In healthcare, they could power prosthetics that feel and react in real time. For self-driving cars, they can process sensory data instantly, making them safer. And for your smartphone, they could run powerful AI without draining your battery. Now, if neuromorphic computing is inspired by biology, our next topic dives straight into the weird and wonderful world of quantum physics. Welcome to quantum computing. Classical computers, from your laptop to the world's biggest supercomputers, use bits. A bit is simple. It's either a 0 or a 1, on or off. A quantum computer uses a qubit. And a qubit, thanks to a property called superposition, can be a 0, a 1, or both at the exact same time. But it gets weirder. Through another quantum trick called entanglement, you can link qubits together. The state of one instantly affects the other, even if they're miles apart. By using superposition and entanglement, a quantum computer can explore a vast landscape of possibilities all at once, giving it an exponential speedup for certain, incredibly complex problems. The race to build one is on. IBM is targeting a 4,000 qubit system by 2025. Google is aiming for a fully error-corrected quantum computer by 2029. And in 2024, Microsoft and its partner Quantinuum announced major breakthroughs in creating more stable, logical qubits. The quantum era has begun. So what can you do with this power? You can simulate molecules to discover new drugs and materials in a fraction of the time. You can create financial models that predict market movements with unheard-of accuracy. You can solve logistics problems so complex that finding the most efficient shipping route for a global company becomes trivial. And while quantum computers could break today's encryption, they also hold the key to creating new quantum-safe ways to protect our data. So we have two revolutions: neuromorphic computing, which mimics the brain's efficient, parallel style for learning and pattern recognition, and quantum computing, which harnesses the laws of physics to solve immense calculations. They are different paths, but their futures might just converge. Imagine a quantum computer simulating a new drug, while a neuromorphic coprocessor analyzes the data in real time, learning which molecular structures are the most promising. This isn't just about making computers faster, it's about creating entirely new kinds of computers to solve entirely new kinds of problems. The march of Moore's Law may be slowing, but the journey beyond silicon is just getting started, promising an era of discovery we can only begin to imagine. Thanks for tuning in to G Fun Facts Online.